Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 7 from the course, but make sure you have watched the previous ones before viewing this one. In this lecture we would be discussing about blackbody radiation, and next we would be discussing about the Planck's quantum theory. So now in the last lecture, we had discussed about the theory given by Maxwell, the electromagnetic wave theory, which basically explained the wave nature of the electromagnetic radiation. Now the wave nature of the electromagnetic radiation could explain some of the experiment phenomenon like diffraction, interference, which we already studied in the last lecture, but it could not explain some of the properties of radiations, such as blackbody radiation, which was basically the nature of emission of radiation from hot bodies. Then it could not explain the photoelectric effect, which is the ejection of electrons from metal surface when the radiation strikes on it. And then it could not explain the variation of heat capacity of solids as a function of temperature. And then the line spectra of atoms with special reference to hydrogen. So we will be discussing them one by one, except for the fact that we would not be discussing the third one. So what is heat capacity of solids? How does it vary as a function of temperature? This is a big topic which needs a great detail to discuss and understand, which we would be doing in some other course, as well as you would be doing this in physics also. So for this course, basically we would be discussing the blackbody radiation, the photoelectric effect, and then the line spectra of the atoms with reference specifically to hydrogen. So let us start the study with understanding the phenomena of blackbody radiation. In this phenomena, the solids, when heated strongly, they emit radiations over a wide range of wavelength. And what do I mean by that? Let us understand this with the example of an iron rod being heated strongly. Right? When an iron rod is heated, it changes color with increasing temperature. And you can see in the diagram also that we have taken an iron rod. We are heating this in a furnace. At some specific temperature, you will see that it starts glowing with a dull red color. Then on further heating, the color changes to more red. It becomes more intense red in color. And on more heating, on increasing the temperature further, we are seeing that the color changes to yellow and then to white, and at a very, very high temperature, the color of the iron rod is blue. Right? So how do we understand this in terms of wavelength and frequency? So we have studied the electromagnetic spectrum, from the knowledge of which we know that the red color radiations, they have a greater wavelength than the blue color radiation. Right? So this means that on increasing the temperature, the wavelength of the light being emitted is decreasing, and the frequency, which is inversely proportional to the wavelength, is increasing. Right? I hope this is clear. And now this was repeated with a lot many solids, and it was found that the color change was consistent at the specific temperatures. So increasing the temperature, you could see the same pattern with any solid. So that way we can conclude from here this also, that this color change was not dependent upon the nature of the material of the solid which we were taking. So let us understand this in terms of the intensity wavelength curves. So we have a graph over here for the wavelength and the intensity of the electromagnetic radiations, or the visible radiations at this point you can say, because we are seeing the visible light. So we see this at two temperatures T1 and T2, where T2 is greater than T1. So what do you find over here is that for the temperature T1, the intensity was increasing with increase in wavelength till a maxima, and then it starts falling with the increasing wavelength. Similar pattern you will see at the temperature T2 also, that first of all the intensity is increasing, it reaches a maxima, and then it starts falling with the increasing wavelength, right? The other thing you can appreciate at this from this graph is that at this maxima of intensity you have a certain wavelength, but when you have increased the temperature to T2, this maxima which we are obtaining, it is at a shorter wavelength, right? So you can see this. Now how we correlate this to the phenomena which we have seen. So the peaks of the wavelengths obtained, first of all, they are temperature specific. At one temperature, we are getting a peak at a certain level, and then at the other temperature, we are getting the peak at another level. So this means that the red radiation, you have seen that it was more intense at a lesser temperature. It was more intense at a particular temperature, and the blue radiation, which was more intense at another temperature, which you saw that it was at a higher temperature. And the intensities of the radiations of different wavelengths, they emitted by a hot body depend upon the temperature. As we are increasing the temperature, the wavelength is differing and the intensity of the radiation is differing, right? So I hope you can understand this. And now this graph, this was found to be the same for all the solid objects. Okay, so it was not dependent upon the nature of the material. So what are the observations now related to these radiations? So we have that the objects made of different material, kept at different temperatures, they emit different amount of radiation, right? So different materials, the amount of radiation is different, temperatures are different, the amount of radiation is different. When the surface of an object is irradiated with the light, which is electromagnetic radiation, a part of the radiant energy is generally reflected, a part is absorbed, and a part of it is transmitted. So what happens when a radiation falls on the surface of an object? Three things happen simultaneously. What three things? First is that a part of the energy is being reflected back, right? The other is that a part of it is going to be absorbed by the object, and the third, a part of it is being transmitted. So what happens? Reflection, absorption, and transmission of the radiation. Now the reason for such incomplete absorption of the ordinary is that the ordinary objects, they are as a rule imperfect absorbers of radiation. So not all of the radiation is being absorbed. A part of it is being reflected, a part of it is being transmitted. So as a rule, all are imperfect absorbers of radiation. And what is that ideal body which can emit and absorb radiation of all frequencies uniformly? That means that all the radiations falling on it of all the frequencies, it can absorb all of it and it can emit all of it. So that ideal body is called as a black body, and the radiation emitted by such a body is called as a black body radiation. But in practice, we do not find any such body. There is no perfect black body known. Carbon black approximates fairly close to a black body, but it is not also an ideal black body. And now how we can understand this phenomenon of black body radiation? You can understand this by taking, say, any solid object which has a very small, which has a cavity inside, it is hollow inside. And then we allow a ray of light to pass through a very tiny hole in the object. So for example, if you take a ball, if you take a plastic ball, you will see that the plastic ball, when you allow the light to pass through a small hole that you make in, you will be able to see the path of light basically in this ball, because a part of it, the light that is transmitted, right? So you can appreciate that there is some light in the ball. But had this not been the case, no light was being transmitted out, then what would have happened? Because there is no other space for the light to come out, there is no transmission. So what will happen? What will happen is that this light, this would be repeatedly getting reflected at various places where it is striking, and then part of it being reflected, part of being absorbed, and ultimately whole of this light which was entering through the small hole, this has been absorbed by the walls, right? So this is basically a black body. And then if no light is being transmitted, if you take something like a solid iron object through which there is no transmission, then you will see that you cannot see anything coming out. You cannot see that the light is coming out from there. So this is a black body example which we can demonstrate as a physical experiment. And you remember here that a black body is also a perfect radiator of radiant energy. So whatever it is absorbing, it can radiate back also. So this you can understand by the fourth observation also, that a black body is in thermal equilibrium with its surrounding. It radiates the same amount of energy per unit area as it absorbs from the surrounding at any given time. What all it is absorbing, it can radiate back. And the intensity of the light emitted, that is the radiation emitted from a black body, and its spectral distribution, that depends only on the temperature and not on the nature of the material of the body. So this is very important, that the intensity is dependent only on the temperature and not on the nature of the material of the body. So now this several attempts, they were made to predict the intensity of radiation as a function of wavelength. The electromagnetic theory tried to explain these experimental results, but because the theory said that radiation of only one wavelength could be emitted by a hot body, irrespective of its temperature, so there should have been only one color that we would have been able to see. So this could not be explained by the electromagnetic wave theory. So now what could not be explained by the electromagnetic wave theory was explained by Max Planck in the year 1900. Max Planck was a German physicist, and he gave a theory known as Planck's quantum theory, for which he even received the Nobel Prize in Physics in the year 1918. Now, he was the one to give the first concrete explanation for the phenomenon of black body radiation. He said that the black body wall is made up of atoms, and atoms, you know, whether they are of solid, liquids or gases, they are oscillating. And the frequency of the oscillations is changed when they interact with the oscillators of the electromagnetic radiation that falls on the surface of the black body wall. Now, to explain the absorption or emission of energy by these atoms, he assumed that the energy is absorbed or emitted by a body discontinuously in the form of small packets. And you remember the wave theory that said that the energy is absorbed or emitted continuously. The electrons, they were emitting energy in the form of electromagnetic radiation continuously, is what the wave theory said. So Planck assumed that the radiation was not being emitted or absorbed continuously, rather the energy that could be subdivided into small discrete packets of energy. And the atoms and molecules, they could emit or absorb energy only in these discrete quantities and not in a continuous manner. And each packet of energy, he called it quantum, and in the case of light, he called it as photon. And now he said that the energy of the quantum of radiation is proportional to the frequency, and this is expressed as E proportional to frequency, or E is equal to h nu. Now you would ask, how is the energy proportional to frequency? So what we remember of the blackbody radiation experiment? What we were doing was that we were heating the iron rod. Hence, what we were doing? We were increasing the energy, right? So, if the energy was increasing, what was happening to the wavelength? Wavelength was decreasing with increase in temperature or increase in energy. And wavelength and frequency, they are inversely proportional to each other. So, we can say that as the energy was increasing, the wavelength was also increasing. Or the energy is proportional to frequency, and now this is equal to h nu, where h is the proportionality constant and this is known as the Planck's constant, and the value of this Planck's constant h is 6.626 into 10 power minus 34 joule second. Converting joules into erg, you get 6.626 into 10 power minus 27 erg second. Or if you take it per mole, then this proportionality constant value is 3.99 into 10 power 13 kilojoule second per mole. Then he said that the body can absorb or emit only one photon or some whole number multiple of it. Energy less than one quantum is neither absorbed nor emitted. And you can understand if you compare it to a person standing on a staircase. A person can stand on any one step of the staircase, but it is not possible for him to stand in between the two steps. He cannot take half a step, right? So the energy also similar to this can be taken as any of the one values from the whole numbers. That is, E is equal to NH nu, where N is 1, 2, 3, but not 1.2, 2.7, 2.5, 3.5, not half steps. They have to be full steps, so it has to be a whole number multiple of the photon. The packet of energy, they have to be whole number multiples. So with this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. And I hope the Planck's quantum theory and black body radiation, both concepts, they are clear to you. So that would be all for this lecture. I hope you really enjoyed understanding all the concepts which we discussed. So please do click on the like link and also do subscribe to our channel H2O so that you get a notification as and when we put up a new course for you. Do click on the bell icon too. If you have any queries, you can mail us at h2ochemistry@gmail.com. We would meet again for lecture 8 on the topic photoelectric effect from the course Atomic Structure on the channel H2O. Bye for now. Enjoy your studies. Have a nice day. Bye bye.